quantum mechanics, people say it's a most wonderful theory and most amazing description of the universe. Yes, that's true. But it doesn't give you a description of the universe which involves significant mass displacements.
Quantum theory says that any object, even a mountain, can exist in two places simultaneously. However, you never see this. Why? Today, I have a huge treat, as this was months in the making. A new experiment which until today was in the pre-publishing phase and is now published. Sir Roger Penrose and Professor Yvette Fuentes are here to talk about the controversial consequences it has for understanding the relationship between quantum theory, collapse, and gravity. My name's Curt Jaimungal, and on this channel I interview researchers regarding their theories of reality with rigor and technical depth. Today, I finally have permission to show you a conversation that spans how Roger sees mass displacements as causing collapse, the difference between active and passive gravity, and the intricacies of this new Ron Folman T-cubed experiment. We also go over Penrose's speculation about dark matter and cyclic cosmology. I traveled from Toronto to film live at Oxford University's Math Institute. I truly hope you enjoy this. I'm joined here with Roger Penrose and Yvette Fuentes. Welcome. Thank you all for coming again.
Thanks.
My pleasure.
Great to be here.
So there's an experiment that's making the rounds. It's pre-published, not published yet. Maybe as of this recording it's published, but it's called the Ron Folman phase experiment. You both see it as extremely important. However, there's disagreement in the field about its interpretation. So before we get to the importance of the experiment, how about you explain what the experiment is, Yvette, and then we'll hear, Roger, why you think it's so important.
Okay. Yes. So it's a very special atom interferometer. So maybe I should start by explaining what an atom interferometer is. So, a regular interferometer, you have a photon and you pass it through what we call a beam splitter, which lets the photon go through one trajectory and then another. It's reflected by some mirrors. And then in another beam splitter, which is a crystal that allows the two paths to interfere. And then at the output of the interferometer, you see interference fringes and with a certain contrast and so on. So black and white interference fringes typical from a wave propagation in the interferometer. So an atom interferometer is kind of the same thing, but instead of using photons, is using atoms. And well, one of the things that I find really beautiful about light and matter interactions is that if you have the atoms being interfered, instead of one uses like a crystal to interfere photons, you use laser fields, so a light field, to make to play the role of the beam splitter for the atoms and so on. So a regular atom interferometer, you would have atoms arriving to the laser that splits the atom. So the atom goes itself in a superposition of two different trajectories. It gets reflected again. Instead of mirrors, there are fields that reflected back so that they can interfere again at another laser, and then you can detect the output and so on. So that's kind of one version of this super famous experiment that was done in the early times of quantum mechanics with electrons, right? That the interference fringes of electrons were observed, confirming that that they behave quantum mechanically, this particle wave duality experiment. So that's now almost 100 years since the Nobel Prize was given to Pauli for that, and so on. But since then, people have been doing interference with atoms. And even with bigger systems, the record is by Marcus Arndt, where he can put molecules in the interferometer and see the fringes and the contrast. Now, what Ron did was a very special type of interferometer, because usually there's two different versions of it. One is the atoms are in free fall. So you take like an atom and you beam split it and you let it fall, but it's in such a way that the atom follows two different trajectories, and then with fields you make it interfere. And actually that's one way in which we measure gravity. That's a gravimeter, because the different sort of trajectories, due to that, the atom picks up information of the local gravitational field, and that's how gravimeters are made. But they're in free fall. Another type of atom interferometer would be in which it's called a guided interferometer, in which you're like have fields to trap the atoms. They're not in free fall, and then you could like separate them and make them interfere again.
Mm-hmm.
So what Ron Folman did is that he did a hybrid version of that, in which he takes the atom. So he starts with a Bose-Einstein condensate made of rubidium-87 atoms, and he cools them down to something like 3 nanokelvin. So this is super cold. It's as cold as we can get things in the lab, in the experiment. And then he makes the atoms go through the beam splitter. But one of the atoms, one of the arms of the interferometer is such that the atoms are at rest. So he basically acts with fields on the atoms such that he cancels gravity, and the atom is just levitating there. And in the other arm, he uses again fields to kick the other branch of the interferometer and let then this atom go in free fall.
Okay.
So this is done with what we call an atom chip. So this is a chip where you can build like a little experiment inbuilt in the chip that produces, you do like wires, and they produce magnetic fields. And the whole system is controlled by this chip through the magnetic fields. So you use a magnetic field to make one of the branches levitate and the other one to give a kick to the atom. So the magnetic fields sort of change the internal states of the atoms to some states that are C magnetic fields and others that are that don't, to produce this sort of hybrid interferometer where one of the atoms is at rest in the lab and the other one is in free fall, and then he interferes them and he sees the fringes. And what he finds in the fringes is that there is an oscillation which has a very special type of oscillation because, oscillations obviously always depend on time, but this type of oscillation depends on the cube of time.
Okay.
Then maybe Roger can explain the significance of that.
Sure. Yes, well, the importance of the experiment, as far as I can make out, I'm not an experimentalist, so I have to judge for what other people say about it. But I gather the idea is, you see, there's a very famous principle called the principle of equivalence. It actually goes back to Galileo, so it's a very ancient principle, which is that you can get rid of gravity by free fall. So Galileo imagined dropping a big rock and a little rock from the Leaning Tower or something like that. And he was well aware that air resistance, if you drop a feather in a rock, the feather will go slower, but that was because of air resistance. He was perfectly aware of that. But if you could remove the air, then the two would fall together. That is to say, if you were in a falling frame, it would just look as though they're simply hovering there and gravity has disappeared. So that the principle of equivalence basically is to say that locally, a gravitational field is just like an acceleration. So you can get rid of it by freely falling. Now that's well known for classical physics from Galileo, and it's a basic principle that when you go to relativistic situations, looking at fastly moving things like that, then Einstein used this as the basis for his general theory of relativity. So Einstein's general relativity was based on this very principle of equivalence, that you can get rid of a gravitational field by simply falling. Of course, if you want to say you can get it freely falling in Pisa, for example, but that doesn't get rid of it in New York. So if you want to have a theory which encompasses the principle of equivalence, that's where Einstein comes in and needs to have curved space-time in order to make sense of this principle of equivalence. But it is the basic principle of Einstein's general theory of relativity. Now, the question is, to what extent is this also consistent with quantum mechanics? And the basic principle is this principle of equivalence. Is the principle of equivalence respected by quantum mechanics? Now, theoretically, you can look at this and say, if you have an accelerating frame, does it look the same as having a force? And it almost does. When I say almost, it's quite surprising how almost it works. Because you can consider two cases. One is that you can consider a quantum mechanical situation where you put a term in the Hamiltonian. That's the technical term for considering you have a force, and you describe that force by putting a term in the Hamiltonian. That's basically what you do. Then you can try it again a different way, which is to consider a freely falling frame, and you do freely falling coordinates. And you see, is the answer the same? Well, it's almost the same. When I say almost, it's a bit hard to explain without knowing a bit about quantum mechanics, but you find that your wave function, the thing that describes the system, differs by a phase factor. That's a number which multiplies your wave function by a number which you can ignore normally because the phase factor doesn't come into calculations of probabilities and things like that. But if you look carefully at the phase factor and you compare it, the free fall case with the gravitational force case, you see that there is a phase factor which is a little bit peculiar because it involves an exponential of the cube of the time. T is the time, t cubed in that expression. And you might say, well, who cares? Because when you're working out probabilities and things like that, this doesn't enter into it. However, it means you really are looking at something a bit different. That the term, to be a little bit technical, it means that your quantum theory is a little bit different. In quantum field theory, you have to start with what you call a vacuum, and you build up your states by putting things into the vacuum. Now, the vacuum state is different in these two cases because of this t cubed term. So it's interesting to see whether quantum mechanics really respects the principle of equivalence in this particular way. And to see that, it's purely theory that you'd expect to see this. Now, does nature really respect this theory? And what's, to me, important about this experiment is you actually see this t-cubed effect in the experiment. So you can see, you can look at the phase by comparing one branch with the other, and apparently this experiment seems to see exactly what you would hope to see if the principle of equivalence is respected by quantum mechanics. And to me, this is very important because it's combining these two great theories of 20th century physics, one, general relativity, which is a purely classical theory, and it's based on the principle of equivalence being true. That's the basic principle upon which the whole theory is based. And when you think about quantum mechanics, you want that to fit in with this framework. And we do see that the way in which it has to fit in was with this curious exponential of a t-cubed term. And you see this in the phase which is observed in the experiment. So it seems to me, although one expects it from theoretical grounds, if you expect but it's important to see that it's really true. And it's not a surprising result in the sense that if you'd expect the principle of equivalence to hold in quantum system too. But the fact that it actually does, and it shows up in this peculiar term, is very important. It also has an importance when you go a little further. And this is not something which, you see, the T-cube term apparently has been seen about 100 years ago. I looked up the old papers and I never could quite see why it's actually doing the same. It's just calculations when you're looking at things in accelerating frames and so on. So you could say, well, it's not that exciting. But that's just the mathematics. You can see you need this term in order to make the acceleration be equivalent to the acceleration due to gravity being equivalent to free something you can get rid of with free fall. But the importance of the experiments, I think, is just to verify that this is true. But it's also important if you take this a little further. This is not part of the experiment, but it's part of what I looked at and what Yvette and I looked at in papers which we looked at, collaborated with later on. And the thing is that if you consider going a little further, by considering some body and its own gravitational field is important. Now, you've got the field of the Earth, and you've got some other body which maybe be putting into a superposition. And you look at it in the field of Earth, and then you think, well, the correct way of looking how gravity is dealt with in quantum mechanics is you say, well, you can get rid of it locally by the principle of equivalence. Now, if you have a body which is put into a superposition of two different locations, is that still true? And the trouble is you can't really do it with an individual body because you can't. The acceleration is different all the way around the body. So you have to sort of look at it a little bit more. But what we do is we say, well, we know that getting rid of the gravitational field by free fall is the correct way of doing it, but you can't do that with a body in superposition because the free fall is different in different places and all that stuff. So what you've got to do is to try and see if you do it there, thinking of gravity as a force and saying, well, that's not quite the right way of doing it, but think of it as a force and see whether there is an error that you can calculate. And then you work out this error and you see that tells you this thing has a lifetime. And that's important because the lifetime of a superposition is that something, if you have a body here and here at the same time, in quantum mechanics, you could have a body here or a body here, and the state with it being here and here at the same time is part of quantum mechanics. It can be two places at once. That's a well-known puzzle about quantum mechanics. But if you have a big body which gravitates, does that give you problems? And yes, it does. You find it gives you, because of all this business with the T-cube and all that stuff, and you see that it does give you a problem. And that problem indicates that this superposition maybe is unstable in a sense, that it will decay into one or the other in a certain lifetime, which would be very exciting to see. I mean, that's going way beyond what one can do at the moment in experiments. But do we see in experiments, and this is the experiment that Yvette is involved in trying to do, can you see effects that show up, well, sort of comparing the gravitational field in effect of the body itself, and does that lead to effects that you can experimentally observe? I really can't go into it because it's rather technical. In fact, I'm not sure I understand it completely. But this is, in Yvette's experiment, is to see whether these effects that should come about from this experiment, whether these effects are there. Now, you see, it's important because quantum mechanics, I mean, people say it's a most wonderful theory and most amazing description of the universe. Yes, that's true. It is a wonderful theory and it gives you an amazing description of the universe, but it doesn't give you a description of the universe which involves significant mass displacements. that is to say, a massive body in two places at once. You're only looking at things where the mass of the bodies can be ignored. And all experiments to the moment which confirm quantum mechanics involve effects where the mass displacements are much too small to have any effect.
Thanks to NOLA Mattress for sponsoring this episode. Head to nolamattress.com/TOE and use code TOE to get an extra $50 off your mattress. NOLA is an award-winning mattress brand known for cooling technology, exceptional pressure relief, and long-lasting durability, all shipped to your door for free. I'm a side sleeper personally, and I've always had two struggles, at least two primary struggles. Overheating is one at nighttime, and then another is finding a mattress that's actually comfortable for extended periods. So I went with the NOLA Evolution King in luxury firm. I just got it a few weeks ago. Here's some footage of me. The difference is immediate. I'm falling asleep much quicker, which for someone who records late night interviews often, it's a huge, huge deal. Sleep is a huge deal. The temperature regulation is also phenomenal. I often run hot when I sleep, same with my wife. And now I'm not waking up overheated, constantly turning my pillow over. And the real test, as I mentioned, my wife loves it. If you're married, you know that matters almost more than anything else. The comfort level compared to our old mattress isn't even close. All NOLA mattresses are made to order at the Arizona facility, no harmful chemicals, no fiberglass, so there's zero off-gassing concerns. I know that's something that my mother-in-law in particular cares about. Visit nolamattress.com/TOE with code TOE for $50 off. That's NOLAH mattress.com/TOE. It ships straight to your door in the US for free. It arrives rolled up in a box, and the setup is trivial. Unbox it and let it expand. You get a 120-night sleep trial, so you have over 3 months to make sure that you love it. Plus, there's a limited lifetime warranty with financing options available. If you're looking for a new mattress, head to nolamattress.com/TOE and use code TOE for an extra $50 off. This is an additional discount on top of what's already being offered on their site. So check them out while you can.
So you want to have an experiment where you're beginning to see this effect. And this was telling us where, you see, quantum mechanics has this problem that it gives you ridiculous answers if you think of it from macroscopic bodies. I mean, why couldn't a rock sitting on the table here be in these two places at once? And according to the framework of quantum mechanics, sure, they could be in two places at once, but you never see a rock in two places at once. And that depends upon going a little further, and you have to say, well, if you consider the gravitational field of the rock, and can that be consistent with quantum mechanics? You lead into certain problems. And these problems seem to indicate that lifetime of a rock being in two places at once, that's a finite lifetime. And for an actual rock, it would be a ridiculously tiny fraction of a second. If you try and put it in this place and this place at the same time, it wouldn't last, would be absolutely instantaneous. It'd become one or the other. And that's what we would experience in actual life. We don't see things in superpositions of two places at once. I mean, people often say, well, the reason you don't is because the environment has got involved in the thing. That's not a real answer. You have to say, why does the environment actually make a difference? And if you go into the calculations, you look at it, no, it doesn't answer the question. It's because the environment is also, it's sort of moved around, yes, and the environment can be most of the movement in the system. And that's why the thing can't be in two places at once, because the environment has been jiggled too much. But there's no experiment yet that has looked at this effect of why quantum mechanics, if you like, gets into trouble with macroscopic bodies. And when you have mass displacements, well, you see, it's a long way from the experiment that has been done, that Yvette was just describing, the one where you have the bodies in free fall and compare it with the one on the table, so to speak, and you see this T cube factor. That's just the first hint of why macroscopic bodies don't behave as you might expect as a quantum mechanical system. And it's the first little clue. That's why it's important. And I think that it's only a little clue, but it's important as being the first little clue, as far as I can see.
So it sounds to me like this Ron Folman T-cubed experiment is testing whether the equivalence principle holds in quantum mechanics. Okay, seems like the answer is yes. It seems to me like it would be more interesting if the answer was no, because that would indicate there's some inconsistency there. And it sounds like what you're saying, Roger, is that Yvette's experiment takes this further to test a collapse model, a certain type of collapse model, namely yours.
Okay, so let me clarify a few things and talk about the experiments that are taking place by other groups, and so to put the whole thing in context. I mean, the reason why Roger says that Ron is experiment is very far away is because effectively the experiment of Ron is with one atom. And maybe it's good to also make the distinguish between passive gravity and active gravity that you usually make. And I think this sort of clarifies things. So you have the Earth active mass, let's say, makes the atoms fall. And then you would say, okay, but then the Earth has a passive mass, but the Sun has the active mass that makes the Earth move around. No, so that was I think it was given by Newton, this distinction. No, so what Ron has is that he has the atom as a passive mass in a superposition in the active mass of the active gravitational field of the Earth, but the field the mass of the system itself is just in superposition in the presence of the field of the Earth. And what Roger calculations and ideas and so sort of he argued is that under that circumstance, the equivalence principle and the superposition principle they're not in conflict with each other. No, so that's exactly what Ron shows, and what Roger was just explaining now, just put in active, passive terms, is that when you have now, forget about the Earth. There's no Earth. It's just the superposition of the atom with itself. So in that case, it's the active mass of the atom in a superposition that Roger pointed out that in that case, there is a conflict between the equivalence principle and the superposition principle that should lead to the collapse. Now, why in the experiment by Ron you cannot measure that is because for one atom, the effect is tiny. So you would have to wait, I think it's 10 to the 20 seconds or something like this to see the effect for one atom. So basically you can just neglect that and forget about it. But the point is that when you start having heavier systems, then this becomes relevant. So Roger and I wrote a paper where we were exploring the possibilities of doing an experiment with a Bose-Einstein condensate. And in that paper, we gave numbers. So usually this atom interferometry experiment, that's a good reference that we were talking about for Ron. The experiment takes milliseconds. That's how long he can hold this superposition. You would need, let's say, if Ron could keep a superposition for a second or two, which is still really far away from what experiments done, but it's not impossible. But in order to see the effects of self-gravity, you would need something like 10 to the 9 atoms in a superposition. So a mass, like for example, could be a lump or like a silicia bead with the equivalence of like, let's say, very roughly speaking, with 10 to the 9 atoms in it. And that's very different to the one atom that Ron had and his impressive. I mean, his experiment is impressive, but tests something different. Now, there has been progress in testing the superposition with massive systems, and like I mentioned before, the record is currently by Markus Arndt at the University of Vienna, where he puts these molecules that have like 2,000 atoms each. Well, but that's the molecule in superposition with itself. But that's the comparison with, I think now he managed to do this with an order of magnitude more, but I don't know. I heard, so I don't know if that's like published yet or not. But last thing I heard was that he managed to take it one order of magnitude further. So let's say something like 2 times 10 to the 4, compared to we found 4 times 10 to the 9. Really far away.
Yes.
And it's very difficult to take those steps by making things more and more precise. And there's many groups around the world working in that direction. Ron Folman himself, he wants to do the experiment with diamonds, which have a lot more mass. But it's very difficult to put solids in a superposition because they're very hot. So they can, for example, Markus can cool down the molecules to, I think it's microkelvin temperatures. And those temperatures are still too hot to see the gravitational effects. But still, there's a lot of activity worldwide because of the importance of this experiment to our understanding of the interplay of quantum mechanics and gravity, that there's many people trying. So they use nanodiamonds, silicia beads, silicia rods, membranes, cantilevers. There's a number of possibilities. But if you see, all of these involved solids, and that's kind of the state of the art and where things are at, no? So now a Bose-Einstein condensate, we were talking about that before. You can cool down to half a nanokelvin. So from millikelvin to half a nanokelvin, that's like a really long, and then you would say, well, why? No, that was kind of the idea. Why not use a Bose-Einstein condensate? So they have another problem. Maybe before I go into Bose-Einstein condensate, I would also like to mention work from 2 other people that I'm like impressed.
Sure.
And another
Please.
one is Markus Aspenmeier, who is also at the University of Vienna. So I spent 3 years there because of these amazing people, because I like to propose experiments and so on. So having the opportunity to talk to the 2 Marcuses, Anton Seilinger is also there. It's just an amazing place to do experiments. Markus Aspenmeier can cool down a bead to quantum scales, and these beads are pretty big. They have like 10 to the 8 atoms. So they have kind of getting the mass right, but he hasn't been able to put the bead in a superposition. So he can cool this big system to the ground state, to quantum scales of a harmonic oscillator, but he's still working towards doing the superposition. And another person that I would like to mention is Hendrik Ulbrich, who's at the University of Southampton.
Okay.
And he's done some really beautiful experiments measuring gravity with these nanobeads. So these are like the smallest sort of systems that they can still measure gravity between 2 different, not just one, it's like 2 different systems. It's not quantum yet, but it's really like their technology is really getting quite impressive. But still very far away from being able to test if gravity collapses the wave function. So we wrote this paper on what could you do with a Bose-Einstein condensate, because could we use as an advantage that you can cool it down to those temperatures. But now, here comes the big problem, is that if you take a Bose-Einstein condensate, what you want to do to test gravity is that you want to create a superposition of the atoms left and right. Actually, I didn't say what a Bose-Einstein condensate is. Maybe I should start there. So take an atom in a well and cool it down to the ground state. So that you do in 2nd year quantum mechanics is the typical example. And it's really beautiful because what you see when you cool down the atom to the ground state is that it becomes completely delocalized in the potential. So it's not just like left or right, it's like everywhere. Now take 10 to the 5 That's like the typical size of a Bose-Einstein condensate for most experiments, 10 to the 5, 10 to the 6, rubidium, sodium, something like this, atoms into the ground state. So the system, because atoms are bosons, the system behaves like a big macroscopic system behaving quantum mechanically. So that's very nice, and people use them for many things. But now the challenge is take the 10 to the 6 to, we need 10 to the 9 actually, to create a superposition of left and right. And that is very difficult because a Bose-Einstein condensate is not a solid, it's a fluid. So in particular, the atoms are not bounded together. And the moment that you lose one single atom from this superposition, all of them left, plus all of them down, that left and right. So you would do this in what we call a double well potential. So people in the lab have already done these double well potentials, like, for example, Marcus Overthaler in Heisenberg. Several people, but I remember him in particular, that you can have these atoms in these double wells, but nobody has been able to do a superposition of left plus right in that way, because if you lose one, the whole thing collapses. And actually, they just haven't. I think the record is 2 atoms or something like this by Chris Westbrook in this situation. So, whereas the temperatures seem to be kind of promising, well, then the fact that the atoms, if you lose one, is so fragile, then again made the possibility look very unlikely. But then, what people actually do in the lab is that they don't prepare these states, which are actually called noon states, because are n on the left, nothing on the right, plus nothing on the right, n on the left, so they're called noon states, is that they've been able to prepare another type of states that are very interesting. So in a double well potential, again, because the atoms are not bounded, you can have the atoms tunnel from one well to the other. Now, the Nobel Prize a few days ago, on the 7th of October,
Right.
Was given to tunneling. And in a different system, right? But the fact that atoms can tunnel through a potential. So what you have in a Bose-Einstein condensate is that in a double potential is that the atoms can tunnel from one well to another. And that gives you like a variety of quantum states that you cannot get in a solid. Because in a solid, they're all bounded together, so you can only do a superposition here. But in a double well, you could do more like a whole family of very rich quantum states. One type are called like 2-mode squeeze states. And this is like superpositions of 1, 1, 2, 2, 3, 3. Like more sophisticated states. But some of these generalized states have already been produced in the lab with quite a few number of particles. So those are accessible to the experiment. So then you would say, why don't you test gravitational effects, active gravity, in those systems that people have already produced that sort of states? Well, because there was no formalism to study the gravitational self-energy for that kind of states. And actually, well, we tried for a while, but now I have developed like a new formalism that allows you to study self-gravity for these new states. And then you can use these easier, more accessible states that don't have the super strong requirement that you would have on one hand on solids, or on the other hand on the new states, to test the gravitational effects. And this is the experiment that Roger sometimes mentions. And I think I should say that the experiment, I'm a theoretician. I figured out how to calculate the self-gravity for this state and proposed the experiment. But the experiment is been done by Philippe Boyer at the University of Amsterdam and Chris Westbrook, who's in Paris. So the team are, us, and with the advice always of Roger. And of course, we have students and so on. So it's a very nice team. I love it. I love working with Philippe and Chris, and of course with Roger. And well, let's see if this alternative route gives us some results, hopefully, in the near future.
Roger, why is this T-cube test? Why is it with Ron Folman? Why is it causing such a hubbub in the physics community among the people who know about it?
I'm a bit confused myself, so I don't think I can answer your question. I think I get the impression that Ron was not quite so... I mean, what I regard as important about his experiment, he was not regarding perhaps as the main feature of the experiment. I'm not sure.
I don't think so. I think Ron is very much in agreement with the importance.
Well, I was a bit puzzled because he was trying to remove the term principle of equivalence from his... he was suggesting, I mean, he's changed his mind. I said, that's ridiculous, you see.
Yeah.
So he seemed to have a somewhat different view about the importance of his experiment.
Yeah.
I don't know. Maybe I've got it wrong.
No, I don't think so. I do think that he sees it in the same light as you do. I think there's been some confusion about it because the point that Roger makes is a subtle one. It's a subtle point, and I think not always is that maybe people working in atom interferometry and quantum experiments are not that familiar with the subtleties of it, and somehow I think it goes somehow overlooked. That's why I think it's great that Roger explains his point of view and so on in this
certainly better
alternative
go along
way.
with it. I mean, he wasn't removing the principle of equivalence, but I just thought the fact that he was puzzled me. That's all.
Yeah.
But it seems to me it's an important experiment, and it ought to be. I mean, it's not unexpected in the sense that when you look at the subtleties of the principle of equivalence in connection with quantum mechanics, we don't.
But that's the case, like with every proposal. Like you propose something, right? That you prove mathematically using the theory. Like what example that I gave about, I took the theory of Berry phase and then put a vacuum state, and and then for me it was like, well, the fact that this was shown was not a surprise because the mathematics and the theory showed already. I don't know very well why there was a controversy about it. Sometimes there's controversies on like the assumptions that you might make in a given proposal or in a different result. But in that way, an experiment confirming like a theory, sometimes they say, oh, well, it was not expected. But it's always like, in a way, a surprise because the theory can have places where it goes wrong, right? Like well, I mean, hopefully not in the mathematics, but sometimes, or more likely, I think, in the assumptions made. So it's always, for me, a big thing when an experiment confirms a piece of theory. But this time it's been like a long time that the theory is quite well established, and finally the experiment confirms it.
Yeah.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount. It seems like we've covered the ground when it comes to the Ron Folman experiment. I'll end with a question that is, I think you all agree or you all disagree, but for the similar reasons. Does the graviton exist?
Oh, gosh. Well, I'd hope so. I'm not sure whether that's relevant to any. That's a different question. Isn't it?
Yes. We're changing gears.
No, well, I would certainly think it has to have, there would be such a thing as a graviton, yes. But you see, gravity in normal experience is so weak. I mean, it's to try and see quantum effects in gravitation are extremely difficult. It's not, it's as a force, it's very, very weak. I mean, it's not really a force even. It behaves differently from other standard forces. So I'm not quite sure what the question is here. I mean, why is gravitons not observable as such?
No. What I'm wondering is, in our first conversation, there's plenty of talk about, well, let's not focus so much on quantizing gravity. Let's quote-unquote gravitize or gravitationalize the quantum. In quantum gravity, the graviton makes appearances, but not in all quantum gravities. For instance, loop quantum gravity doesn't have a graviton. We also should have talked about...
I'm not sure about that.
We should have talked about spin networks, actually.
Yes.
That's another conversation.
Yeah.
Anyhow, I wanted to know if, because of the way that you view the world, as in gravitizing the quantum, it doesn't seem like there's room for the graviton to exist.
No, I think that's a bit misleading. That's not my point of view. The trouble, gravitons should exist. It's just we're so far away from anything which would see the... gravitation is such a you see it as a macroscopic thing. I mean, the fact that we're sitting down on the Earth here, sitting down in our chairs rather than floating around, is because there's an enormous Earth. You have to have something that big in order to see the effect. And so if you want to try and do an experiment in a lab, which is looking for the quantum effects of gravitation, is hugely far off. Doesn't mean I don't think there are such things as gravitons. It just means that the effects of the particle effects of gravitation are so far away from anything one could see in an experiment. It's all right to talk about them, and I do sometimes. But what we see is gravitational fields. And the fields are but you see, gravity is different in many respects. It doesn't even have an energy momentum tensor in the same way that ordinary things do. I mean, you can force it into it, but it's not. I'm not sure. So I'm not answering your question, really. You see, I think there's a whole subject which doesn't really exist, and I haven't quite thought of a good name for it, which is, I would say, big physics, but big is the wrong word. I'm trying to think of the right word.
Penroseology.
No, that's not the right word. No, it's something to do with it being on a huge scale. You see, what is the biggest stuff in the universe, in a sense, including the biggest mass? Well, it's dark matter. All these particles that we talk about, which are so important to our existence and experiments that are done and all that stuff, they're trivial correction, if you like, to the big stuff in the world. Now, what's the big stuff? Well, the big stuff is dark matter, which in my view is a form of gravity, and gravitons. Now, they're big stuff. So that to treat them quantum mechanically is a way, way off, you see. I mean, it may be that dark matter particles decay in a way that conceivably could be observed. That would be very exciting if that's the case. But it's a different world almost. I mean, it's not a different world because we're sitting down here in chairs which are, we're not floating around because of gravity. But it's a different world from the particles and the which behave very quantum mechanically when you go discuss them. But they're a trivial modification to the big stuff, which I'm trying to say. I need a better word for it than that. And the big stuff would be gravitation and dark matter, basically. And cosmological constant in some form comes in. And that there's a whole world of how to describe all that stuff. And the matter is a sort of perturbation. But it's, of course, very important and to us. And our lives are dominated by the small stuff. But I don't know the right way to talk about that. So
you could say dominating stuff, no?
Well, it's certainly dominated. You see, the dark matter is the main stuff. You know, in the solar system, in the galaxy, it's the dark matter. Now we don't have a proper theory of it. I mean, it's very far from the small stuff which we're made of, and we're a perturbation. If you consider the overall effect of it, we're a little perturbation to what's happening to the big stuff. So it needs a theory of big stuff. And that's really what I'm trying to think about mainly, at least on the physics side. Because the cosmology is very much driven by that kind of thing. Of course, you do have matter playing a role as well, but it's more like a perturbation to what the big stuff is doing. I don't think I'm going to call it big stuff. That's not a very good term. I would need a more. What do we need? Something. A grander term. Grand. You could call it the grand stuff. I don't know. It's not quite stuff.
Yvette, does the graviton exist?
I think so, yes. I think gravity should be quantized, so I would disagree with my colleague Jonathan Oppenheim on that. By the way, I love his work. Like, I am a fan of what he does, although I disagree, that gravity is classical, like he proposes. But what I really love about his work is that he comes with his own idea on how would you unify, let's say, a gravitational theory, which is more like stochastic.
Whose work are we talking about?
Jonathan Oppenheim from UCL.
Oh,
yeah. Well, I mean, what he's done that I like is that he proposes an experiment. So that's what I admire of his work. Well, and I also that he comes up with his own idea on how to unify gravity and quantum mechanics. But he does it. He says that gravity should not be quantized, but it's more like a stochastic thing. But then he proposes an experiment. And that's why I love his work so much, because that's it where I want things to go. That we start being creative, we come up with our ideas, we propose things that can be tested in the experiment. And then since experiments are really getting so, I mean, they are amazing, and they can go, well, when people would do entanglement on tabletop experiments. Now, Anton Seilinger has been able to do, demonstrate entanglement across thousands of kilometers using satellites. I mean, you see the progress has been really amazing in many different directions. So I think that we have to make use of quantum technologies and these improvements in order to find ways of testing the theory. And like we were talking before about how some things maybe look impossible, but if you find the right angle and the right way to pose things, then maybe they're more at reach. I also maybe gave you an example of how to do with these states that are kind of the states that already people do in the lab, or another example of thinking things in a different perspective, no? So I do think that gravity should be quantized. And I do think that there's a particle, that mediates. I don't know if the graviton is, as in other, candidate theories propose, but I do think that there might be such a thing, yeah.
Something that interests me about you is that you propose interesting experiments. Popper is often misquoted as saying that if your theory is falsifiable, then it's scientific. It's actually the opposite. If your theory is scientific, then it's falsifiable. It's a necessary condition, but it's not a sufficient one. I could imagine a theory or a theorist who says, okay, I've predicted supersymmetry is going to come on at 14 TeV. And then it doesn't. And then they say, okay, they work away and then they say it's going to come on at 14.5 TeV. And so they're making predictions and perhaps they're even proposing experiments, and then it doesn't show up. And then they'll say 15 TeV. I'm just imagining right now.
Yes.
If that's a word. I'm imagining right now. Okay, so what makes a good experiment? What makes a good theorist who proposes good experiments? Because what I just said, I imagine isn't great science.
I can't tell when an experiment is going to work or not. I mean, that's business. I mean, sure, it's got to be testable. I mean, a theory which is not. But you see, it doesn't have to be experiments. When I talk about big stuff, what's the biggest stuff pretty well that's ever, not the whole universe, but is these wonderful observations due to Alexia Lopez. Huge rings of galaxies. Absolutely enormous. They're so big that there wasn't enough time in the age of the universe to make them that big. When I say the age of the universe, I'm talking about the normal view about the age of the universe, which is starting with the Big Bang. My view is that there has to have been something prior to the Big Bang which would cause these. Now, this is observational. I mean, they're not experiments in the sense that Yvette's doing. I mean, you've got your lab and you observe, testing certain things that you can test in a lab. These are out there in the world, and you're observing what's there. And you have to take what's given to you. But some of these effects tell you maybe something different about the universe from what you thought previously. And I think these rings that Alexia Lopez has seen, when she's seen, I mean, the techniques are very important, which she happened to use in order to make these observations. But apparently, I should say, there are several times the diameter of the moon, you see. You're looking at, if you could actually see these rings, they would make a big thing in the sky. Really enormous. And she's found 3 of them, apparently. The ones that were in the news more recently. Well, first it was a ring. No, actually, she found the arc. There was an arc and then a ring. And then I was in email contact with her, and she said she thinks the arc is actually another ring. So there are 2 rings. And I heard recently that she's found a 3rd one. Now, these huge things were not predicted by anybody, not even by me, I should say. So although when I heard about them, I thought they were very exciting because they seemed to confirm the fact that there was something prior to what we believe to be our universe. And they would be something like the collisions between enormous supermassive black holes. You see, you expect to see this in the remote future. You've got galactic clusters of galaxies, and these clusters of galaxies that we see in our universe, they're so big. Well, I should say first that a galactic cluster does not expand with the unit; they remain bound. So as the universe expands, these clusters remain more or less bound. But then the stars in them gradually get swallowed by black holes, and the black holes get bigger and bigger and bigger and gulp out most of the stars. And then occasionally you get a few big black holes which will run into each other sometimes. Absolutely enormous black holes. And they will send out a signal of gravitational waves And these gravitational waves, according to the view I'm trying to promote, will come through from the previous eon into ours and could well trigger seed the galaxies which we now see. It would be an enormous effect which would trigger the creation of new galaxies. And these galaxies could be in the form of what we see as a ring. So I found her observations very exciting, because although I hadn't thought of this as an observational test, thinking about it later, it's a very good indication that there was something before the Big Bang. I'm only saying this really in the context of our conversation. There's a whole area of not so much experiment, but observation. I mean, okay, the telescopes that they make and the techniques that are used to see these rings. For instance, there's a new technique where you look at magnesium lines and you're looking at absorption lines in magnesium, and that tells you the presence of galaxies. I don't understand it fully, but they tell you the presence of the galaxy. So you don't see these rings. You see them only by the absorption lines in these magnesium, and you look at more distant quasars and the light from them, so on and so on. But all I mean is there are a lot in the way of observation. Okay, it's experiments to some degree, because you're maybe sending a satellite out there which can see effects that you wouldn't see just from sitting on the Earth. It strikes me that there's a whole other area of observational physics, which tells us something about the structure of the universe and about the contents of the universe. Because these dark, well, I think it's the dark matter. I have a view which I'm still not quite formalized, which has to do with how gravitons, where you see you asked me about gravitons. Yes, I do believe that gravitons should be there. On the whole, when it looks at overall effects, so you don't see individual gravitons, but there's another particle, which would be the dark matter particle, which I refer to as an eribon. This is I think that, well, I've used this term in papers. So.
I like that name very much.
Wait, sorry, repeat that name?
Eribon. Well, you see, there's Erebus or Erebos. Who is the god of darkness. He's a very ancient, way before. He's not even a god, because the gods were more recent. You see, I don't know about.
It was a good idea to call the party.
He was a pre-god, I think. Well, he was. I think what was it? Chaos. Yes. You see, chaos was. This isn't physics at all. This is
it's
Greek
just
mythology.
a nice word.
Yes, it's a nice word. So I thought the eribon was a good term, because it is the god of darkness. You see, and he was way there with chaos right at the beginning. You see,
as a student, I found how sometimes physicists are very good at finding very beautiful names for horrible to calculate things. Now I was so much looking forward to learning what's charm and what's strangeness. It sounds like wonderful. And then when I actually had to do some calculations, I was like,
yes. Well, some of the names are dreadful, I think. I mean, dark energy to me is a dreadful name, because it's neither dark nor is it energy. It's certainly not energy. It's in the wrong place when you put the energy momentum business. It's not energy was a certain spot in that thing, and this is not that at all. So it's certainly not energy. It's not dark. It's invisible. The dark matter suffers from the same thing. It's not dark. It's invisible. I mean, if you look at galaxies, you see dark ring. If you see a galaxy edge on, you see maybe there will be a black line along the middle. Now that's dark. That's dark stuff. But that's not dark matter. The dark matter you can't see at all. It's invisible. And that's a quibble. I think dark energy is worse than a quibble. I think that really is a bad name. I just heard somebody on the radio was saying what a wonderful name it was, and he'd only thought of this, and it just fits so well, and all that stuff.
I wanted to say something about the experiments. Actually, I wanted to mention 2 experiments. I think the comment I wanted to make is how difficult sometimes is to rule something out. So DOC came up with the idea as well. Roger and Lajos DOC came up with this idea independently, that gravity collapses the wave function. But DOC took it a step forward and wrote down a stochastic model that predicts more the detail of the collapse, but it does not conserve energy. So one of the predictions of the model is this radiation that should be observed. And there's been a really beautiful experiment done underground by Catalina. Can you remind me how to pronounce her name? She's done these experiments underground, with a big...
Oh, this is the heating.
Yeah.
Spontaneous heating, yes.
So she's done an amazing experiment to test not only DOC's model, but a whole bunch of collapse models. And they haven't seen the signature of these models, right? So up to certain parameters, these models have been ruled out. But, models usually depend on a parameter. So then you could say, you can't really say, that's it, the models are dead because we don't see, because there could be some other scales. And so that's a bit of a difficult thing, but you were asking me what would be good proposals or no, and I think a little bit that at least you can test a big part of the parameter space in a realistic way. But yeah, we have to live with the fact that sometimes ruling out things can be very difficult. Yes, and let me mention one other example, because I find this very relevant to the discussion and also a beautiful proposal. So Sugato Bose, a colleague of mine, who actually I used to work with him when I was here at Oxford in a junior research fellowship. He proposed an experiment that is to test quantum gravity. So I think he builds on something that Feynman proposed before, but in a time that you didn't have the advances of the quantum technologies that we have now. And then Sugato takes it, and Sugato and colleagues take it further by kind of stating how would you do this test nowadays, right? So the idea is that you have one particle in a superposition, but not only one, you need a second particle in another superposition. So you see already the challenge that we've been talking for a long time of getting one in a superposition, and here you need two in a superposition. But anyway, so this side of the superposition you bring to get close to the other side of the superposition. And the idea is that if gravity entangles these particles, then gravity is quantum, because what the work done by them claims is that you need a quantum mediator to entangle. Now, I'm not going to comment on that because there are discussions and some people agree on if that's the case, or some people disagree on what the case, and there's a discussion. I don't want to chip into that discussion. What I want to talk about is the course in relevance to the question that you asked me about the experiments. No, also we were talking about how I put my bar really high sometimes. Yes. That experiment is much more difficult to do than other experiments that I proposed in the past, like the gravitational wave detector and things like that. And that's where I say I've kind of said I'm maybe not going to push on this because that is really far away the line. And this is an example of an experiment that is really difficult to do, but you have a huge community working on it. And why not? I think they should be working on it because you find creative ways to overcome hurdles, and then you're successful. Example is LIGO, right? At the beginning, there were so many sources of noise, and then the community comes together, works together. You come up with new ideas on how to solve some of the problems, and there you go. They detected gravitational waves. So I'm very supportive of the experiment that they proposed and with the community following it. But it is a difficult one. But let's say you have this situation. Now let's say that DOC and Roger are right. and gravity collapses the wave function, right? So they're never. That doesn't mean that gravity is not quantum, but in my opinion, but they're never going to be able to test that if gravity collapses a wave function, because actually it happens at similar scales. So if Roger is and Yossi are correct, and gravity collapses the wave function, boop, boop, they're going to collapse that superposition. And then they won't see the effect proposed by Sugato and Bose and others. But that doesn't mean that what they're proposing is not there. What just would mean is that the scales at which this effect exists are still pushed to scales where it's even more difficult to see, right? Because the scales where Sugato says that these things would get entangled are the same as the ones we would expect to see the collapse of the wave function. So if collapse happens, then you don't get entanglement because the state collapsed. But the state could still be getting entangled before the collapse at other scales that are maybe more difficult to access in the experiment. So you're not ruling out. So that's the thing, is that what we're looking for doesn't rule out the other experiment. It just, so I think that's kind of an interesting thing about when is an experiment, when is a theory completely ruled out or not? No?
Thank you both for coming on.
No, thank you very much. It's been a big pleasure talking to you as always, and especially with Roger.
No, it's always been great fun. Thank you. Yes. Yeah.
Curt here. I'm glad you enjoyed that. I'm inferring that you enjoyed that because you're continuing to watch all the way up until this point. Now, it takes a huge amount of time to prepare for interviews like this. I study the guests' papers, I study adjacent fields, I construct quizzes for myself, and then perform those or test myself for weeks prior. I then also talk to the guests' colleagues often so that I ensure that I have the guest's point of view correct in my head and that I'm not wasting the guest's time or your time. It also takes a considerable amount of money to travel from a place like, say, Toronto to Oxford to film with Roger, or to film at Boston, at MIT, or Harvard. People think that YouTube ad revenue is high. However, in science and philosophy, they're one of the lowest paying categories. So I directly rely on the support from generous donors, such as potentially yourself. If you have the funds and you're willing, then there are 3 primary ways to contribute. One is to become a founding member on Substack. Of course, becoming any paying member on Substack is great, but the founding member is the top tier. Number 2 is giving a one-time donation via PayPal. And number 3 is to give a one-time donation via crypto. Links to all of these are in the description. Many people think that Theories of Everything, this channel, is a huge team, it's a huge production. Actually, it's just 2 or 3 people. It's myself and my wife, and of course the full-time editor who is editing this. Thank you. And that's all to say that your donations go a long way. Thank you for getting us over 500,000 YouTube subscribers. That's magnificent, and it's all thanks to you. Thank you.